Mila, and we'll be presenting the work that has been done around the BabyAI platform.
Thanks for coming on this very cold Friday morning to talk. So the BabyAI project is a project that's focused on embodied agents and granted language learning. The name BabyAI comes from Yoshua's long-standing vision of having an AI agent that learns like a baby. Something that he's been thinking about for a long time, as far back as the original curriculum learning paper in 2009, and probably before that as well. The long-term goal of the project is to have some kind of a personal assistant, so maybe like a household robot that you can talk to and commands to, and that you can also teach using a limited amount of demonstration. Because presumably, if you have some kind of personal assistant, you will need to teach it new tasks that it doesn't know about and about the specifics of your environment. So obviously, if you want to be able to teach a robot, say by demonstration, the biggest constraint that we have is the amount of data that a human being can really provide. So how many times, for example, would you be willing to try to show a robot to make a sandwich? Maybe 10 times, maybe 20 times, but probably not 1,000 or and right now we're very, very far from this. So John McCarty is credited for having created the term AI back in 1955. And at the beginning of the AI field, people were very excited. They thought that we were very close to having artificial intelligence that could understand natural language. There was just a matter of programming the right logical reasoning rules and programming common sense into machines. And they thought that this was a matter of just like inputting the right facts, and we could basically translate our human knowledge of the world into programming code. And kind of like the pinnacle of the excitement was about the time that Winograd did his PhD thesis and created this Shroodaloo project, which was kind of a simulated world where you could type natural language commands and tell it to manipulate blocks and also ask it questions and it'll answer. He just got people really excited that if we could just scale this approach, we would be able to have robots that can understand natural language and deal with the real world. But obviously, this didn't really pan out. The researchers at the time kind of overpromised and under-delivered. And this led to the famous AI winter. Nowadays, we have the promise of end-to-end language learning with deep neural networks. There's been some impressive work done, for example, by DeepMind. And the promise of end-to-end language learning is that with very little engineering, say with just reinforcement learning, you could train an agent to understand any kind of language just from raw sensory inputs. This is a very seductive idea. But what's the catch? Well, the catch is that for this work, they needed about 2 million reinforcement learning episodes to learn what's actually, in fact, very, very simple language. Probably even simpler than Winograd's thesis. So there's a question about scalability here. Like, could you actually scale this to more complex tasks? I'm not sure. And obviously, if we wanted to have a human teach an agent about a task that, because some tasks maybe are not realistic to simulate. Like for example, could you program a dishwashing simulator? Could you really get all the details of the physics involved into a simulator? So we'd really like to improve upon this. So with respect to the question of scaling, there's also been the work on embodied question answering back in 2017. So in this environment, you have like a virtual 3D house, and you have a question that the agent has to answer. And the agent has to navigate in the house in order to find the information necessary for answering. This is using reinforcement learning. And unfortunately, the problem is extremely challenging and the results were very poor, which I think goes to the idea that this end-to-end language learning approach, at least if you do it naively with a simple model and just like throw lots of people at the problem, it doesn't. And similarly, in the world of text-based games, people have tried to train reinforcement learning agents to solve mud games. So those are kind of like text-based role-playing games where an agent interacts with the game through something like natural language. And kind of the story here is very similar. Like the results so far are not very impressive. Yes. Multi-user dungeon. So at the time, you could like remotely connect into a server with telnet. The BabyAI platform is a platform to simulate grounded language learning, which focus on studying sample efficiency. You might be thinking, well, there's already many platforms that try to do instruction following and this sort of thing. I think the BabyAI BabyAI platform is unique in that we tried to have a more principled approach to how we generate the language and how we design the levels. So BabyAI, you can think of it as kind of like the clever of instruction following. And the platform comprises a GridWorld that's partially observable, language that's compositional and natural language-like that tries to be like a subset of English. And there's 19 different levels of increasing difficulty, and we also have a heuristic bot that can solve all the levels. So why did we go with the GridWorld? Why didn't we go with something like a 3D environment like DeepMind has been doing? Well, so the design of BabyAI is kept intentionally minimalistic, as in we wanted to have a setup that has enough complexity so that we can study the relevant research questions, but ideally no more. Just as complex as possible, but no more, because that makes it easier to control all the relevant factors. It's also faster to modify, customize, and iterate with a design that's simpler. And I think there's kind of an argument to be made that the problem is already extremely challenging as is. So maybe we don't need the added difficulty of working with a more complex environment when we're struggling to make progress in this problem area. Another reason why we chose to go with a GridWorld is because it's very lightweight and efficient. And for running the experiments that we did for the iClear paper, we actually needed several thousand GPU hours of compute time. And even though it's just a GridWorld, we do try to maintain some similarity to the real world. So we chose to make the GridWorld partially observable, and we have some basic constraints like the agent can't see through walls. So the BabyAI has 19 different levels of increasing difficulty that form kind of a curriculum with the goal of teaching the agents to master the baby language. And each level is basically like a family of different missions that share a similar structure. So for each of these different levels, each one is kind of a different OpenAI gym environment, and every episode is different. So every episode, the agent is given an instruction that it has to execute, kind of like in the same family. And we've attempted to design the levels based on a principled decomposition based on the skills that the agent needs to master in order to master. The BabyAI is a natural language-like. It's meant to be understandable by human and to be approximately a subset of English. It has a compositional structure and it's generated from a context-free grammar. So this is different from other instruction following frameworks because typically what they do is they just use like a template-based approach where you have like a fixed sentence structure and you have some holes and you plug in different words in there. And the grammar is actually very simple. It's only like about 8 clauses. But despite its simplicity, there's more than 10 to the 19 possible instructions. And it has interesting compositional properties. onto the BabyAI levels, like I said, they form kind of a progression. And this is one of the simplest levels that we have in BabyAI. It's called go to obj. And in this level, all the agent has to do is to go to an object. So here, the little red triangle is the agent. It can turn left, right, move forward. And the area that's highlighted is the part of the world that the agent is able to see. So in this environment, all that the agent has to do is to go to an object, and there are no distractors. And this level basically doesn't even involve language because the instruction is always the same. The agent only has to learn to navigate to that object. Then if we progress a little bit, we have another level called go to red ball, which is the same as go to obj, but now there's distractor objects. The agent has to learn to navigate around these objects and also to distinguish the object that it has to go towards from those distractors.
Yes, you say that every episode, in the previous example, for instance, you have an episode, you have like traces in this location, and also from the goal. I mean, what is it that changed?
That's right. So in this level, the position of the red ball would be different, and the agent would constantly start in a different position orientation. With the goal here being that this forces the agent to generalize a little bit better.
And the dimension of the grid is exactly the same with the tablet also changed.
In our environments, the size of the grid is fixed at the moment. And then, yeah, so these first two levels don't really involve language. Then we have a level called go to local, which is the same, but this level is kind of the first level where you need to master language. You need, because the instruction tells you which object you have to go to. And so the progression keeps going like that. Eventually, we have language that talks about locations. Here, pick up the red key behind you, or pick up the purple key on your left, and so on and so on. And then we have some levels that involve navigating around a maze of 3x3 rooms. So this maze has doors, and the agent has to do some amount of exploration to find the object that it has to navigate to, and the instruction tells it which object to go to. And then furthermore, we have some levels that involve like a sequence of instruction that the agent has to perform, and eventually navigating to find keys and unlock doors and so on. Yes. The way it works is the agent sees like 7x7 cells in front of it. So we structured it that way because we wanted to kind of approximate the way that humans perceive the world in the first person. Can you repeat? You can only see if the door is open. If the door is closed, it blocks the agent's vision. So as I was saying earlier, the levels are split up based on the competencies that are required to solve them. We distinguish 13 competencies. So the maze competency is like being able to navigate in a 3x3 maze. Unlock means being able to find a key to unlock a door. Location is like understanding words like in front of, behind you, etc. And so basically the levels form like a directed acyclic graph of competencies required to solve them. And this culminates in the boss level that requires all the competencies to solve. And the boss level has instructions like open the door and pick up the green box, then pick up the green key and put a blue ball next to the gray ball. Yeah, so the goal of the project, or main goal, is to be able to study sample efficiency. And in order to do this, we wanted to be able to have a simulated teacher so that we could generate an arbitrary number of demonstrations, basically. So we had this idea that we would train a reinforcement learning agent to solve the levels, and then use the reinforcement learning agents to generate demonstrations. And then use these demonstrations generated by the reinforcement learning agent to train a second agent using imitation learning. And we can measure how many demonstrations does the second agent need to master the task, basically. Unfortunately, we run into two different issues. The first is that Reinforcement learning right now struggles to master the most difficult BabyAI levels. We can crack the simpler ones, but the boss level, we only get to around 80% success rates. The second one is that from what we've seen so far, our reinforcement learning agents generalize fairly poorly. In particular, they generalize poorly to states that they haven't seen before. So if we want to use a technique like Dagger, where we let an agent navigate around the world, and then when it picks like the wrong action, we want to have an expert provide the correct action. That's difficult to do with reinforcement learning because reinforcement learning will learn it will learn a policy for the states that it typically visits. But if you put a reinforcement learning agent in the states that it doesn't normally visit as part of its learned policy, it just doesn't know what to do. So the solution that we came up with for this is basically that we would program a bot using heuristics and kind of classical AI. Because our world is so simple, we figured that it would be possible to just hard code an agent that can solve all our levels to a 100% success rate, and that can suggest actions at any possible states. Crucially, the most important feature of the bot is that it handles partial observability. So it's important that the bot doesn't just have like complete knowledge of the environment, because if the bot is basically omniscient and it sees everything that's in the environment, then it will generate demonstrations that are basically impossible for an agent with partial observability to imitate. And the way that this bot works is that it basically has a stack of sub-goals. The reason it has a stack of sub-goals is so that it can interrupt what it's doing and execute a sub-goal and return to what it was doing before. So for example, if I tell you go to the blue ball, you're going to have to explore the environment in the hopes of finding the blue ball. And maybe as you're exploring the environment, you find that there's a door that you have to go through, but there's an object that's in front of the door. So in order to go through that door, you have to take that object and move it away. So we push like a sub-goal on the stack that says unblock the door. And once the door is unblocked, presumably you want to go back to what you were doing before and go through that door. Possibly at a different point, you find that the only room that you haven't explored yet has a locked door, and so you need to go and find the key to unlock the door. And then so that pushes a sub-goal on the stack that says go find the key. And once the key is found, the agent comes back, it will finally unlock the door and go back to trying to explore the rest of the environment. So this bot is relatively simple, but as far as we know, it's unique for this kind of platform. So the first question we wanted to answer is just how difficult are the BabyAI levels? So we trained an agent that has a kind of a vanilla network with a convolutional neural net, and it uses film for attention. It has a group with attention for instructions as well, and an LSTM for memory. So we generated 1 million demonstrations using the bot, and we trained a different model on each level for a week. And these are the results that we have. So as you can see, we were able to crack all of the smaller levels, the levels that are basically within one room, but the harder levels we're not able to quite completely solve. And there's kind of a loose correlation between the number of steps that the agent has to perform in the environment and the success rates, or I should say inverse correlation. And how is sample efficiency? What we wanted to do was to try to measure how many demonstrations an agent needs to be able to solve a level to 99% success rates. The reason we put the bar at 99% success is because having an agent that can perform something with 40% or 80% success rate is probably useless for most applications. So we really wanted to measure like mastery of the level. And we also wanted to have a metric of success that's easy for people to relate to. So I was reading a paper the other day about Mujoko Walker agent, and the paper said that the agent had a reward of something like 14,397. And when I look at that, it means nothing to me. Like if you haven't used this environment, it's like I don't know how far can your agent walk? How fast is it? You know, those are the questions that I would like to be able to answer to have some idea of how effective your method is, or how useful it is. So basically, we split our data set of demonstrations into like smaller data sets in different intervals, and we try to measure how many demonstrations of agents that's doing imitation learning needs to crack these levels to 99%. And we also measured how many reinforcement learning episodes we need to get to 99%. Here, all the numbers are in thousands, and what we can see, which we suspected before, is that even for the very simple levels, we need a surprisingly large amount of demonstrations. Even a very simple level like go to red ball needs between like 44 and 62,000 demonstrations to solve. And also the number of demonstrations increases very quickly as the complexity of the task goes up. And in terms of imitation learning versus reinforcement learning, we see that there's maybe like 1 order of magnitude difference in terms of the number of episodes needed to solve the task, which is a smaller difference than we had originally anticipated. Then we did a curriculum learning case study. So basically, we pre-trained an agent on a base level, and then we tried to further train this agent on a harder level that requires a superset of the competencies required to solve the base level. And then we measured how many demonstrations were needed to train on that second level. The question we're trying to answer is basically how much does pre-training help? How much faster can we learn with pre-training in this way? And the answer is that it's not obvious. Basically, doing curriculum learning right is very tricky. And it really works best when you're going from a base level to a target level that's a strict superset of the first task. And when you have like a really small increment. So the right pre-training can help a little bit. The wrong pre-training doesn't help. It's not always obvious what the right pre-training is. And when it does help, it doesn't help by a lot, so less than an order of magnitude, unfortunately. Yeah?
This is literally just pre-training and then
That's right.
And I was also wondering, you wonder where the pre-training differs.
Yeah, so here, for example, go to local is where you have to go to an object in one room, and go to is where you have to go to an object in a maze of 3x3 rooms. So you would expect that go to local teaches the agent a little bit about language and about recognizing the different objects, and that you would think that this pre-training would help. In practice, in our setup with kind of like naive reinforcement learning, it doesn't help so much. And I would say that the main problem that I see is that reinforcement learning learns policies that are reactive, as in you're really learning to map pixels or observations to actions. And when you change the distribution of your observations, it tends to transfer very poorly, unless those distributions are really, really close. So going from go to local to go to, you're dealing with like a visually very different environment, and so the pre-training doesn't help. At least not with this method. I feel like there has to be a way to make this work. But the naive approach doesn't work so. And then because we're thinking about learning with a human in the loop, we wanted to do a little experiment with interactive imitation learning. So basically, if we had a teacher that could change the way the data that it provides to the learner based on what the learner is doing well on, could we get better data efficiencies that way? So the way we did this is we started with a small training set of demonstrations, and then we interactively generate new demonstrations specifically for missions on which the agent fails. and we grow the data set by 20% at each step. So the idea is you're feeding the learner more demonstrations for the tasks that it's doing the worst on. And the results that we got were again a little mixed. Like we found that it generally helps, but not by a lot. Right? So interaction can help, but probably not enough to really make a difference. So in conclusion, data efficiency is something that really needs work. Hundreds of thousands or even millions of demonstrations are needed to solve even very simple tasks. We've observed also that it takes about 3 times as much data to get from 95% success rates to 99%. And we're obviously extremely far from the point where we can put a human in the loop. We've also found that poor generalization is really a major issue with deep reinforcement learning. Yeah, and we hope that maybe you'll use BabyAI for all of your data efficiency stuff. It's a simple domain, and it's also a very convenient sandbox that offers some very challenging tasks despite the fact that it's so simple. But the fact that it's very simple is also what makes it appealing, because it's very easy to customize the platform for your exact research problem. And if you do use BabyAI, we hope that you're not going to cheat, as in the goal is not to over-engineer solutions that only work in GridWorld. The hope that we have, at least, is to be able to have solutions that generalize to more complex environments as well.